Today I want to explain about the star cluster. Let me share my screen. Yeah. We have different kinds of HR diagram or Hertzsprung-Russell diagram. We have two kinds of them. For example, log G in x-axis and log luminosity in y-axis, or temperature luminosity diagram. And the other, it is the same, like a T effective, like a luminosity. And the other is color magnitude diagram, color in x-axis and absolute magnitude in y-axis. And you see here the both types, temperature, luminosity, color, absolute magnitude. And here you see the main sequence of stars, and here you see the main sequence of white dwarfs. And in here, for example, for our sun, the path is like this. It goes here, it goes to red giants, and then go to white dwarf. This path for our sun. And you see Gaia HR diagram of sources with low extinction, satisfying the filters described in the paper. And here you see for a paper, maybe you see that in Pleiades and in Persephone, it's a good fit for isochrone and for main sequence. But if you see it in close-up, you see, for example, in Pleiades, no, it's not a good match for isochrone in main sequence. Also in Persephone, you see that also it is not a good match for isochrone in main sequence. So if you see a paper like this, you should have it in close-up view like this. And you see then that they do not have a good fit in isochrone for main sequence. Color and T-effective. Measuring accurate T-effective for stars is an intensive task. Spectra needed and model atmospheres, spectral energy distribution or SED fitting, only useful if measurements in the ultraviolet are available. Magnitudes of stars are measured at different wavelengths. Color calibrations goes to give us the T-effective. The ASIAGO database and photometric systems, or ADPS, lists about 200 different systems. And here you see different kinds of filters, photometric systems. And for example, if we want to have to see that where is H alpha, it is H alpha, where is H alpha in different photometric system, where we see that here we have, for example, H alpha, and we search about different photometric systems. As I told you, we have around 200 photometric systems. And we see, for example, which one has H alpha line in the photometric system, and then we can choose it. For example, you see that Washington, ISO, Johnson, and Hubble Space Telescope, they have this kind of filter for H alpha. And here you see Vega. In Vega, Vega is a hot star, and for hot star we mostly have ultraviolet, and we can detect it in ultraviolet. Then we have, for example, sun, and you can see that we can see it in visual magnitude. And then we have M5, that is a cooler star, and mostly it is in infrared region. Here, for example, we have Johnson-Cousins photometric system, or Strömgren and others. You see in different kinds of spectra, lines, Persian continuum, for example. Various calibrations can be used to provide the color relation. Remember that observed B minus V must be corrected for interstellar extinction to B minus V0. Most of the calibrations are for cool type stars. For example, we can measure 4 of them, some of them, and then have a mean from these ones, these 4, and then have a get the mean value to see that how is the photometric of that. And you see that different kind of photometric system, they give different kinds of lines, fits, different kinds of fits. Absorption, extinction, or reddening. There are 3 words for one definition. It's for example, we are observer, and there is a star far away from us, and between us as observer and the star there is some dust and gas, and photons or flux captured or absorbed by dust, and so we cannot see the light of that star completely. General extinction because of the interstellar medium or ISM characteristics between the observer and the object. Differential extinction within one star cluster because of local environment, and both types are in general wavelength dependent. Here you see that in ultraviolet, it is depends on the size of the grains, and if the size of the grain is different, we have different kinds of bands. For example, in ultraviolet, they are larger in wavelength, and in infrared, they are less in wavelength. And we can say that reddening or extinction or absorption depends on mass and wavelength. And RFV is the normalization factor, which is 3.1. And be careful, different values used. It is depending on the line of sight. And you see here the ratio of absorption over extinction. We can say that absorption is for 1 filter and extinction is for 2 filters. If we have 2 filters, we use extinction, and if we have 1 filter, we use absorption. And here you see the difference of them. Also here, you see for different bands, we have different wavelengths and ratio. Absolute magnitude, M defined as apparent magnitude of a star if it were placed at a distance of 10 parsec. Or we can say all flux and magnitude normalized to a distance of 10 parsec in astronomy. V minus MV minus AV is equal to 5 log D minus 5, where D is in parsec. V minus MV is also called distance modulus, and magnitudes are measured in some wavelength. To compare with theory, it is more useful to determine bolometric. And the magnitude, bolometric, defined as absolute magnitude that would be measured by a bolometer sensitive to all wavelengths. We define the bolometric correction to be BC is equal to mm bolometric minus mmv, or visual magnitude. Bolometric luminosity is then becomes like this formula. And bolometry is not dependent on luminosity and metallicity. And here, if we have just V minus V with 0, it is absolute distance modulus. But if we have reddening AV, it is apparent distance modulus. So this formula is for apparent distance modulus. And if we have not AV or reddening, and then we have V minus MV 0 here, it is absolute magnitude. Here you see different kinds of stars. For example, our sun is here. It is near to 0, and these are hot stars. And we can see that bolometric is more useful, and we can detect it more and measure it more in high and more luminous and high stars, or hot stars. Here you see the highest and Ligeti age is 8.90. The distance is 45 parsecs, and metallicity is Fe iron over H. Hydrogen is 0.17 index. And you see that the width of the main sequence about 1.8 magnitude in MMV. What is the reason of that? Then I will explain to you about how and why the reason that we have some width in main sequence for heights. Here we can say that also we can say that for high rotating stars we have more luminosity than less rotating stars. And if we have less metallicity, we have more binary systems. For example, globular clusters are more dense, so we cannot measure proper motion, so we cannot estimate correctly the number of binaries in globular clusters. And all flux and magnitude normalized to distance of 10 parsec in astronomy, as I told you. And for binary stars, magnitude in width in HR diagram is MV is 0.753 magnitude, because molecular cloud was not homogeneous in metallicity. The original molecular cloud was not homogeneous in metallicity. And you see here color magnitude diagram. Here is for Persephone. As I told you, you see the elements, others, stars in the Persephone. You see the Fe iron is minus 4.28 to minus 4.62 dex and 0.34 dex. Here you see the isochron for 10 million years, and we can say that metallicity can change the isochron. So isochron is dependent on metallicity. And you see that for different metallicity, we have different isochrons. And here we can see the magnitude in width for main sequence is plus minus 0.7. For magnitude for main sequence, yes, is 0.3 plus minus until 0.6. Here we have reddening. For example, we can detect a star here, for example, in F7 and the 0.5 color. And but because the star has reddening, so it is not here. But in fact, the star has some shift and has some reddening. It is maybe it is here in A0. It is A0 type of star. So you see here that reddening has some influence in shift, some shift for some stars. And here we can say that in pole there is more rotation to generate more flux energy in equator, and poles are the same. Scientists for a long time looked at the pole of the Vega and they didn't see any rotation. But in fact, Vega has a high rotation in its equator. And here you see, we can see there is a breakup velocity. Breakup velocity is if stars rotate very fast, gravitation cannot hold together the stars anymore. Gravitation cannot keep the star. So it will lose the hydrostatic equilibrium. And here you see the Vega and a summary of physical parameters for the pole and model. And with different metallicity, we have different magnitude and luminosity changes for high rotating stars. And here is a differential rotation. And as I told you, with different metallicity, we have different magnitude. And we should look at the spectral line to see the rotation effect. High rotating stars have more luminosity than less rotating stars with the same temperature. And the effect of rotating can change the magnitude to 1 magnitude. So you see that the rotation can have some influence in magnitude up to 1 magnitude. So we can back to the question that why in HR diagram there is a width. There's a width because we have differential reddening, which means not all stars have the same extinction. Some shifted a little. Spectroscopic binaries, there are binaries. If we have two binaries, with the same temperature, they are more luminous. Metallicity, that we can see that there are different luminosity or absolute magnitude because the stars have different metallicity. And at last, rotation, which changes the magnitude up to 1 magnitude. Binary fraction. It is important for the formation and evolution of star clusters. Critical parameter for the initial mass function, or IMF. It's needed for n-body numerical simulations. Observations are based in many respects. and many different types of binary systems. You see here different kinds of stars. For example, for our sun, that we have a single star, it is like this. And we can say that if we have lower metallicity, there are more binaries. If we see a single star, then look in 0.753 above of that to detect a binary star. How to observe the binary fraction? We have different kinds of solution for that to observe the binary fraction. Photometric observations for star clusters, cluster main sequence, eclipsing binaries, and position astrometric binaries. And for cluster main sequence, as I told you, if we see a singular star, then we can look at it in 0.753 above that to detect a binary star. Spectroscopic observations, radial velocity variability, and detection in a spectra. And if we see two spectral lines in a spectrum, there is a binary system there with mass ratio of 1. Here you see the simulation with randomly distributed mass ratios. In left and in right, you see the observations of precipent with known binary systems. You see? And observe binaries with the Gaia data release 2. In left, you see the distribution of the probable members of NGC 752. And in right, you see the color magnitude diagram of the probable members. You see we have main sequence and there are binaries, which is parallel to the main sequence. We have this open cluster NGC 752. If we draw the plot of that in HR diagram, we see a main sequence, and then we see a binary which is parallel to the main sequence. Here you see the member stars in blue together with field stars in gray for UBC8, which is open cluster, in galactic coordinate L and B, in left and in proper motion space in middle. And the color magnitude diagram shows the sequence of the identified members, outline and empirical isochrone. Let's see. And if we see the binaries, if we want to see that if there is a binary or not, we should observe for a line time. For example, for it is a bin size of 1 day. For 1 day, we can detect something like this, periods, and number of systems. But if we extend the time and observe for longer time, for example 100 days, we see more than this. If you compare it, you see that there are more. And if you observe for 10,000 days, you see the changes of the number and period. Then if you compare, you see a huge difference between them. So reasons for open clusters, we can see that in open clusters, if there is high percentage to see the binary systems, system in open classes are more, has more percentage. But in globular cluster, it is less. As you see, the numbers are so low. What's the reason of that? We can say that in globular clusters, we see less binaries because globular clusters are more dense, and we do not have good proper motions, so we cannot measure whether the stars are in binary systems or not. Also, we do not have good spectroscopy and we do not have good radial velocity. So we can just measure the eclipsing binaries and estimate the value of possible binary by scaling the number of eclipsing binaries. Thank you for your attention and see you next time. Bye.